Today, we're going to pull back the curtain on something that protects just about everything you do online. From sending a text to your online banking, we're talking about encryption. Now, I know it sounds super complex, but at its heart, it's all about solving a really, really old problem. How do you keep a secret?
So let's travel back in time for a second. Imagine you're in class and you need to pass a note to your friend. The mission is simple, right? Your friend has to be able to read it, but you definitely don't want that nosy classmate or even worse, the teacher to see what it says. Well, believe it or not, that exact problem is what encryption is all about. Okay, so let's build on that note passing idea. What if instead of just folding up the paper, you put your secret note, meet at the tree house after school, inside a special little box? And this isn't just any box. It's one that can only be opened with a very unique key. A key that only you and your friend have a copy of. This simple idea, the locked box, is pretty much the foundation for everything we're going to talk about today.
Yeah, that whole locked box thing, it actually maps perfectly to the core parts of any encryption system. So you can think of it as your secret sharing kit. Let's open it up and see what the basic ingredients are. First up, you have the plain text. That sounds technical, but it's not. It's just your original message, the one that anyone can read. In our story, it's the actual note you wrote down. It's the secret you're trying to protect. Easy enough, right? Next up, and honestly, this is the most important piece of the puzzle, is the key. The key is that shared secret. It's the special piece of information you use to both lock the box and later to unlock it. It's the one thing that separates your friend from literally everyone else in the world. No key, no message. And that brings us to the final ingredient, ciphertext. This is what you get after you've used the key. It's the scrambled, unreadable version of your message. Think of it as the locked box itself. Anyone can see the box, they know something's inside, but they have absolutely no idea what it says. The message is literally hidden in plain sight. So, when you put these three things together, you get a really logical flow. As you can see in this table, there are two main processes. You've got encryption, that's taking your plain text, adding the key, and getting ciphertext. That's you locking the box. And then you have decryption, which is just the reverse. You take the ciphertext, use that exact same key, and boom, you get your original plaintext back. That's your friend unlocking the box. So this brings us to what is maybe the biggest takeaway of this whole section. The box can be made of steel, the message can be top secret, but the security of the entire system, it all comes down to one thing, keeping that key safe. If somebody steals your key, they can open your box. It is truly that simple. The key is everything. Exactly. So we get the what, right? We need our plaintext, a key, and we end up with ciphertext. But what about the how? Like, what's the magic that actually happens inside that box? What are these clever little tricks that scramble the message so well? Well, it turns out pretty much all encryption, no matter how fancy, boils down to two really basic ideas. You've got substitution, which is basically just swapping things out, and then you have permutation, which is all about shuffling things around. Let's take a closer look at each one. Okay, let's start with substitution. The absolute best way to picture this is with one of those old school secret decoder rings. You and your friend agree on a secret setting, that's your key, and then every letter you write gets swapped for a totally different one. A becomes D, B becomes Q, and so on. A really famous and simple example of this is called the Caesar cipher. Here, the key is just a number. So if the key is 3, you just shift every letter 3 spots down the alphabet. As you can see in the table, A becomes D, B becomes E, C becomes F, and you just keep going. You're swapping each letter for another one based on a simple secret rule. The second trick, permutation, is, well, it's even more straightforward. Imagine you write each letter of a secret word on a tiny piece of paper. Then you just toss them in a hat and shuffle them up like a deck of cards. All the original letters are still there, but because they're all jumbled up, the word is completely unreadable. So for example, right here, the word hello can easily be rearranged to become something like low hell. See? We haven't actually changed any of the letters. We just messed with their positions. The meaning is totally gone just by shuffling the order. Now here's the aha moment. Whether you're swapping letters or shuffling them, there is one golden rule that can never, ever be broken. The whole process has to be reversible. Your friend has to be able to use the key to unshuffle the letters or turn the decoder ring back to the starting point. This means encryption only hides information. It never, ever destroys it. Okay, so that's a perfect pivot. Decoder rings and shuffling cards, I mean, those analogies are great for understanding the logic. But how does a computer, which only thinks in numbers, actually do any of this stuff? Let's dive into how this all works in the digital world.
Right. Computers don't see letters like A and B. They see the entire world in binary, a language made up of just zeros and ones. So to handle our text messages, they use a quick two-step translation. First, they use a standard dictionary, you'll often hear it called ASCII, to look up a character and find its matching number. Then they convert that number into a unique string of binary code.
And you can see exactly how this works right here in this table. The computer sees the letter A, looks it up in its ASCII dictionary to find the number 65, and then represents 65 with the binary code 0100001. It does this for every single character, every space, every punctuation mark, until your whole message is just one long string of ones and zeros. And this leads us to the final, really critical insight for this section. When a computer encrypts your message, it's not shuffling the letters of hello. It's taking those exact same ideas, swapping and shuffling, but it's doing it with math on that enormous string of binary data. All encryption is just math on zeros and ones. All right, we have covered a lot of ground, from secret notes in class all the way to binary code. So for anyone studying this, maybe for an exam, let's pull everything together into a quick cheat sheet. These are the absolute must-know takeaways. So here are the 4 big ideas. First, the basic framework. Plaintext plus a key gives you ciphertext. Got it? Second, the 2 main tricks are substitution, which is just swapping, and permutation, which is just shuffling. Third, that golden rule, it's useless if you can't reverse it with the key. And finally, always remember, computers do all this amazing work on binary code, not on the letters themselves. And that leaves us with one last, kind of mind-bending question. We've seen that the core ideas are actually pretty simple, right? Swapping and shuffling. So what is it that makes the encryption protecting your phone right now so incredibly, ridiculously difficult to break? Well, that is a secret for another time. Thanks for watching.